Welcome to the first module in this NPTEL massive open online course on estimation for wireless communication. So, this is a MOOC on estimation or estimation theory. So, what we are going to focus on in this course is estimation, more generally also known as parameter estimation, for typically for wireless communication scenarios. For wireless communications, right. So, this is a massive open online course on estimation theory, and specifically estimation theory and as is applicable and applications of estimation theory on wireless communications, in wireless communication systems. And the wireless communication systems we are going to focus on are basically MIMO, OFDM wireless communication systems, and also wireless sensor networks. So, the concepts that we are going to focus on and the applications that we are going to look at are going to be focused towards wireless communication systems, MIMO, OFDM wireless communication systems. Many of you must be familiar with this concept, this of MIMO, which stands for multiple input multiple output wireless communication systems. And also another important group of systems is OFDM, or orthogonal frequency division MIMO OFDM systems, that is multiple input multiple output, and OFDM, that is orthogonal frequency division multiplexing, that is MIMO OFDM based wireless communication systems. And also wireless sensor networks. We are going to look at applications of estimation theory in wireless sensor networks. That is another important area where concepts of estimation are widely applicable. So, we are going to look at wireless sensor networks. Or these are also basically abbreviated as WSN. Wireless sensor network is basically a group of sensor nodes connected over wireless links. That is, these wireless sensor networks contains a large number of sensor nodes which form a network, and these sensor nodes are connected or can communicate over wireless links. They typically measure various parameters such as the temperature, pressure, humidity, etc. And then these measurements are communicated over the wireless sensor node, typically to a cluster head, typically to a fusion center or a cluster head, from which they are disseminated to basically other devices and so on. So, wireless sensor networks have also found a large number of applications for various things such as health monitoring, etc. And wireless sensor networks are an important area in wireless communication. So, basically wireless sensor networks consist of a large number of nodes. These consist of a large number of nodes connected over wireless links. These nodes, these are also known as your sensor nodes. In the sensor network, these are the sensing nodes, or these are the sensor nodes. And estimation theory, the concepts of estimation that we are going to have look at in this course have applications in both MIMO OFDM wireless communication systems and also wireless sensor networks, which are currently evolving paradigms or current research areas, active areas of interest in current research in wireless communications. So, let us basically start looking at estimation theory or concepts of estimation. To start with, let us consider a simple scenario in a wireless sensor network with a single sensor node. So, let us start exploring this area of estimation or estimation theory by starting with what happens in a simple sensor network with a single sensor node. So, I have a sensor node. So, let us say this is my sensor node, which is sensing a phenomenon. This is your sensor node, and each sensor node is basically what it is doing, it is sensing, or it is sensing a phenomenon by making appropriate measurements. So, this sensor node is sensing the phenomenon by making a measurement of a parameter which are going to denote by h. This h is also called, we are going to call this h as a parameter. This is the parameter of interest, and it can represent any component that is being sensed, any phenomenon that is being sensed, such as for instance the ambient temperature, the pressure, the humidity, etc., so on and so forth. So, this parameter h represents any phenomenon that is being sensed, example your temperature, pressure, humidity, atmospheric content of various gases, various pollutants and so on. So, this parameter that is being sensed can be any particular parameter that is being sensed by the sensor network. So, the sensor node is making a measurement of this parameter, that is h, and these measurements and then subsequently processed and then can be sent to a fusion center, or they can be directly sent to a fusion center. Alright. So, this is denoted by the parameter h. So, the sensor node, this is making an measurement, or what we will also call as an observation. So, this is making an observation of the parameter h. Now, frequently these observations cannot measure the exact parameter h, but these observations are going to be affected by the noise. So, these observations are typically noisy. So, these are called the noisy observations. So, let us say I denote my observation by h, y. So, this is my observation y. The observation of the parameter h is typically going to be affected by the noise v. So, this v represents your noise, h represents the parameter as we have already seen, and basically y is your observation, which is also your noisy observation. So, the model that we have, which we are going to employ throughout, is that the observation equals parameter, that is your parameter, plus noise. The observation is basically a noisy observation, and the observation is basically equals the parameter, that is noisy observation y equals the parameter h plus the noise, which is v. We are going to use this model and basically refined versions of this model as we go through this course on estimation for wireless communication. So, the observation is typically modeled as the parameter h in the presence of the noise v, and typically this noise v is typically, this is Gaussian noise, typically this is Gaussian noise, again a very common model for the noise, that is the noise is Gaussian in nature or normal, Gaussian, which is normal, that is the noise has a probability density function, that is noise has the PDF, that is probability density function, which is Gaussian or a normal probability. This is the probability density probability density function, the PDF of the noise is, the PDF of this noise V is Gaussian, and any Gaussian, that is this noise V is basically a Gaussian random variable, and any Gaussian random variable is characterized by a mean and a variance, and typically this noise is going to be, we are going to assume this has mean 0 and variance sigma square. This noise V is 0 mean that is the expected value of V equal to 0, and further the variance of this noise that is expected V square equals sigma square, and since this is expected V square, this is also basically the power, the variance or the noise, the variance or the noise power is sigma V sigma square, and therefore, this is Gaussian with mean 0 and variance sigma square. This is denoted as script n 0 comma sigma square, where basically this 0 denotes the mean, this sigma square denotes the variance of the noise. So, what are we saying? We are saying we have this noisy observation model of the parameter h, the observation is y equals h plus v, and therefore, and we also assume that this noise v is basically Gaussian noise, that is the noise has a PDF or a probability density function which is Gaussian with mean 0 and variance or basically power sigma square. Now, one can ask the question, if the noise V is Gaussian, what is the probability density function of the observation y? Yeah. So, we have y equals the parameter h plus v, and we said we are going to assume that this V is Gaussian noise with mean 0 and variance sigma square. Now, what is y? What is the probability density function? What is the PDF FYY of the random variable y, where y is basically, recollect, y is the observation. So, what is the PDF or what is the probability density function of y? And now, you can see basically V is Gaussian and the parameter h is a constant, it is an unknown constant. Therefore, when V is Gaussian and you are adding a constant to a Gaussian, the output, the probability density function of the output or the observation is going to remain Gaussian. Therefore, y also has a Gaussian, it is a Gaussian random variable. The observation y is a Gaussian random variable. I am going to denote this by RV, stands for random variable. So, this is output is a Gaussian random, output is a Gaussian random variable. Yeah. And what is the PDF, what is the mean of y? Now, look at this, we have Gaussian noise V which is 0 mean, to which a constant h is being added. Therefore, the mean is shifted by the value of this constant which is h. Therefore, the mean of y is basically nothing but h, because V, the noise, is 0 mean. Therefore, the expected value of y, remember the expected value of y equals expected value of h plus v, which is y, which is equal to the expected value of h plus the expected value of v. We have already seen that this is basically 0 mean. So, expected value of v is 0, h is a constant. So, its expected value is h. Therefore, we have expected value of y equals h. Yeah. Now, what is the variance of y? And that is also easy to see. The variance of y is the expected value of y minus h, that is the quantity y minus its mean whole square, that is y minus the mean of the expected value of a random variable y is expected value of y minus the mean, that is h whole square. But y minus h is again v, that is nothing but the noise, because y equals h plus v, y minus h equals v, therefore y minus h equal to v, therefore expected value of y minus h square is expected value of v square. But from above we already know that noise variance is v is sigma square, which means expected value of v square equals sigma square, therefore this is the variance of y is also sigma, therefore the variance of y is basically also sigma square, therefore y, we have y is also a Gaussian random variable which is denoted by script n, the mean is h and the variance is sigma square, and this is an interesting result, that is the noisy observation y, which is basically the parameter h affected by the additive Gaussian noise. The noise v is additive and is Gaussian in nature with mean 0 and variance sigma square. The noisy observation y also has a Gaussian probability density function, it is Gaussian in nature, but its mean is h, where h is the parameter, the variance remains unchanged, that is the variance is sigma square, and we know from the expression of from the knowledge of probability and random variables that the probability density function of a Gaussian random variable with mean h and variance sigma square is given as, that is this probability density function fy of y with mean h and variance sigma square is given as square root of 2 pi sigma square e raised to minus 1 over 2 sigma square y minus h whole square. That is the probability density function of a Gaussian. Remember, this is the probability density of a Gaussian PDF of Gaussian with mean h and variance mean h and variance sigma square. So, that is the probability density function fy of y, which is given as 1 over square root 2 pi sigma square e raised to minus 1 over 2 sigma square y minus h square, that is the probability density function of the observation y of the parameter h in the presence of the additive Gaussian noise v of mean 0 and variance sigma square. However, now we come to the framework of estimation, now we come to the motivation for estimation. Realize that this parameter, this mean which is h is unknown, this parameter h is unknown. This is the parameter, remember this parameter h corresponds to the temperature or pressure, this parameter h is unknown, that is the parameter, let me write this clearly, the parameter h is unknown, the parameter h is unknown. Therefore, we would like to estimate this parameter, that is one would like to find out what this parameter h is. That is the whole idea behind a sensor network, that is we would like to know what is the ambient temperature or what is the ambient pressure. Therefore, one would like to estimate this unknown parameter h, or one would like to compute this unknown parameter h, that is known as estimation of the unknown parameter. So, this is basically one would like to estimate. So, basically we are motivated from this noisy observation estimate the unknown parameter h, and this is basically known as, let me just write it in block letters, this is basically the central idea behind this course. This is basically known as this is basically known as parameter estimation. So, this framework where you are trying to estimate this unknown parameter h from the noisy observations, that is y, remember y is a noisy observation of this parameter h that is made by the sensor. So, trying to estimate or trying to get knowledge of this unknown parameter h from the noisy observation, this is basically the framework of parameter estimation, and we are going to focus, and basically this is going to be the focus of the rest of the modules in this course, that is how to estimate this parameter h, that is estimation of this parameter h from the noisy observations, that is we have our noisy observations y, how to estimate this parameter h from the noisy observations y, that is going to be the focus of the, that is going to be the focus of the that is going to be the focus for the rest of this course. And this broadly basically basically forms the framework or the area of parameter estimation, and as we already said in the beginning of this module, that it has a wide variety of, that is it has wide application in basically both cellular networks in the context of 3G and 4G, third generation and fourth generation cellular networks which employ MIMO, that is multiple input multiple output, and OFDM, orthogonal frequency multiplexing communication systems, and also wireless sensor networks which employ a large number of sensor nodes basically which are measuring these different parameters such as temperature, pressure, etc., and are communicating these measurements over the wireless links to either the cluster head or the fusion center. So, this module basically sets up the initial model, the preliminary model for estimation, which we are going to refine, develop and look at different estimation different models as well as different techniques, strategies for estimation of these parameters, and as well as the performance of these various schemes that we are going to use for estimation in wireless communications, both in wireless cellular networks and also in wireless sensor networks. So, let us stop this module over here. We will continue with other aspects in the subsequent modules. Thank you very much.